Welcome. We continue in our topic, most favorite one, on machine translation. And I suppose it will be in a more technical applicational way. So welcome and take.
So my name is Tamkina, and I'm going to be talking about domain adaptation in machine translation. So this will actually not describe my work exclusively, but it will describe the teamwork that we did at the CLSP workshop this summer. As you can see, the team was rather large, so I'm not going to be able to talk about everybody's contributions. So this is basically like a selection of things that relate to what I did and that I considered interesting. But everything is interesting, and you should definitely read the final report when it's out. So what can we, what should we do about domain adaptation in MT? So domain shift causes translation quality to degrade. That's a well-known fact. And there's been a lot of research concerning how to fix this, how to improve domain adaptation. However, there has been very little work on actually analyzing what the problem is. So we know that the translation quality drops, but the exact reasons why are not well documented. So one of the parts of what we did was to analyze the sources of errors, and then well, you're going to see the results. What actually the biggest problems of domain adaptation are, and an interesting question is also, the previous approaches, did they address these problems, or did they address a minor part of the errors? Another larger area that we worked on was to include machine learning techniques for domain adaptation in MT. This is not usually applied in machine translation because the pipeline of a normal MT system is really complex. It's full of heterogeneous models that interact in the log linear combination, but we can't really, it's not a classical machine learning setting, so we can't, there's no way to straightforwardly apply the classical techniques from domain adaptation. So we developed the phrase-sense disambiguation for domain adaptation, and this is a classical standard machine learning setting where we can use these approaches. And last but not least, there are many open problems when going to a new domain. There are going to be out-of-vocabulary terms on the source side. There are going to be out-of-vocabulary terms on the target side, meaning new senses of words that we already know. And how do we find them? Well, finding new senses is a little more tricky because as you can imagine, it's easy to identify a source word that is unknown. You simply don't have it in your training data. But actually identifying that an existing word has a new sense is a challenge in itself. So I'm going to be talking about the first two topics here. And my work was actually only concerned implementing phrase-sense disambiguation in the decoder. And even not the whole thing, but only phrase-based. But then again, hierarchical code was similar, was adopted basically, and there was a lot of extensions specific for Hiero. I'm not going to talk very much about that. Okay, so what's phrase-based MT? For those of you who didn't know, this is a really, really short introduction. How do we do phrase-based machine translation? We take a lot of parallel data, and we word align it using unsupervised learning. So we can ask the model that we get questions like, what's the probability of car given German word auto? And then we get a phrase, then we use the word alignment to train a phrase table, which is based on the heuristic rules, how to extract phrases from word alignment. And we can ask different questions of this model, like what is the probability of a fast car given ein schnelles Auto? Then an orthogonal model to this is the language model, that only operates on the target side, and questions like how probable is the sequence of words a fast car in an English sentence. All of these models are combined in a log linear model, and their weights are tuned towards a metric of MT quality, such as blue. So this specifies the complete model for machine translation, and decoding then is just the search in the hypothesis space for the most probable translation. So the translation with the highest score according to all these scores from the little models and the weights. And possible settings in domain adaptation are many. Surprisingly, in all of those, you kind of assume that you have enough data in the old domain. It's hard to say what it means, but usually you have a lot of data that you have trained your system on, and then you are asked to translate a different domain of the text where you have only a limited amount of data available for that. So we actually, the different parts of the team and the different sub-projects worked on different settings, but what I'm going to talk about mostly concerns the setting in bold, namely enough old domain data, some amount of parallel, and a similar amount of monolingual data in the new domain. So what are the current approaches to domain adaptation? What can we learn from? What can we build on? So the baseline approaches are quite simple. Just use the old, just use the new data. Or you can concatenate them, and this is not going to work very well because mainly, like usually you won't be able to get much further above the performance on the old domain. And if the new domain is very new, like very different, and you have very little data, then you actually will decrease the translation performance, like even compared to using just the new data. So the typical scenario how to combine models in domain adaptation is to train separate models for the new domain and for the old domain. Well, you can train separate phrase tables, you can train separate language models, and then you simply use the minimum error rate training or some other algorithm to tune the weights and to decide which of these models should be more important, should be less important. This is one of the earliest approaches, and it fits very well into the MT framework as we use it today. Other approaches are concerned with weighting the data or filtering or selecting it somehow. This is usually based on some measure of similarity with the new domain. Like metrics from information retrieval can be used, such as TF-IDF, or various, there's a lot of literature on this, and the approaches vary in many ways. One of the important difference between all these approaches is the level of what you give the weight to, or what you filter, what you select. You can select subcorpora, you can select individual sentences which are similar to your new domain, or you can even do this on the granularity of phrases. And another technique that I like is self-training, which is kind of a trick. You can use the target-side monolingual data to create synthetic parallel data simply by using the old domain or some baseline system to translate the monolingual data into the source language, and then train a phrase table on these fake parallel data. And this actually works for domain adaptation. So this, of course, concerns with this. This is mainly the setting that you would apply it to is when you have a lot of monolingual data and only some parallel data or no parallel data at all in the new domain. Okay, so what data sets did we use? We had 5 domains in total. The old domain was always Canadian Hansard, and the new domains were EMEA, News, Science, and Subtitles. Okay, so EMEA, that's data from the European Medical Agency. That's mostly drug prescriptions and usage conditions and things like that. News, that's a news commentary corpus. And Science, that's these are papers and abstracts from various areas of science, like physics and computer science and things like that. And Subtitles is just film subtitles. You can see that the last domain is kind of special because we have a lot of sentences in Subtitles, but as you see on the token level, it's similar to the old domain in size to Hansard. So that's, of course, because the utterances in Subtitles are usually very short. And there are a lot of new words in Subtitles, and you can probably imagine what kind of words. It's colloquial, let's say. And yeah, so Subtitles is a little special. We actually, for most of the time, worked either with EMEA or with Science. So how do we analyze what's the source of errors when going to a new domain? We developed a taxonomy of errors. called S4 analysis, and the error types are seen, sense, score, and search. So the seen error refers to source side out of vocabulary words. In the new domain, we have a word that we haven't seen in the old domain. We don't know how to translate it. The sense errors are more subtle. You know the source word, but none of the translations that you've seen in the old domain applies in the new domain. The score error is simply when you decode and search for the most probable hypothesis. You could find the correct one, but you won't because you have different probability scores. So the decoder will actually prefer something else and will discard the correct hypothesis. And search is a category that we actually didn't work very much with, and that's because we found out that its effect is very, very small, and this refers to the situation when the decoder would actually know how to produce the correct translation, and if it searched in the space without errors, it would find this correct translation, but because of pruning, it will discard it during decoding. And we used this taxonomy of errors in two scenarios. The first one was a macro analysis. This refers to creating some synthetic experiments, which we then using which we measure the individual errors. So first you create two systems. The old domain is just take all your data from the old domain and train a phrase table on this. And the mixed one is a mixture of old and new domain data. What it is, it's you concatenate the old and the new domain data, but you do a linear interpolation of the probabilities and of the scores, that's it. The interpolation is tuned using like a grid search towards blue score. And how do you then use these two phrase tables to determine the errors, the error sources of errors? So the seen errors, the first type, is quite easy. You just add the unknown source phrases from the mixed phrase table to the old and see how much improvement in blue score you get. So you take this old phrase table, you look at all the source phrases in mixed which are not in the old phrase table, and you just add them. And you evaluate the baseline system, you evaluate the system, and based on the difference in blue scores, you can infer how much error did you does it actually cause. Yes. Yes.
And then this special one for the scene.
Exactly.
Diagnosis.
And actually, we also tried not only adding those phrases to old, but also subtracting those phrases from the mixed table. And the results are quite different, but I'm not going to complicate things. Hopefully, there will be a paper published about this soon. And sense is similar, but we don't look on the source side. We look at the target side. So we simply add all those phrases with known source side but unknown target side to our old phrase table. And score is a bit more complicated. We have to take an intersection of old and mixed. This corresponds to phrases that are known both in the old domain and in the new domain. And then we only exchange the scores. So the first time we use the old scores and measure the blue score. And the second time we take the probabilities from the mixed phrase table and measure the blue score again. And as I already said, the search effect was negligible because we did an experiment. We increased the beam size and increasing it, so like eliminating search errors, did not improve blue score at all, suggesting that perhaps search errors are not as important in this setting. And the results are kind of one of the I think important results of this workshop, because as you saw in the previous approaches, a lot of them just concerned themselves with improving this area, like modeling the score better. But actually, if you look at the scene errors and sense errors, it's apparent that we should actually try to translate words that we don't know, or find new translations for words that we do know. So this is like equally important part of the research in domain adaptation, and it should be done, and it hasn't been done, at least not much of it. And one kind of marginal case is the news domain. You can see that like improving the news table doesn't give you much, and our explanation is news is actually not very different from the Hansard data. So no matter what you add in terms of vocabulary or in terms of probabilities, you don't get much further than just by using the old domain. But in the domains that are more different, you can see that the picture is consistent. Scores are important, but equally important are the source and target side of the vocabulary terms. Another analysis that we did is called WADE, or Word Alignment Driven Evaluation. It's actually a name of a dog that accompanied us during the workshop. So what do? You use word alignments between the input and reference, and between the input and the output of machine translation to check whether words are mapped to correct translations. So you can kind of align the reference and the empty output via the input, and then look at the alignment types. And we annotate the alignment types with a number of categories. One of them are the correct alignments, meaning we produce the right word. OOV error, we produce the wrong translation and the correct one isn't in our phrase table. OOV freebie is an interesting category. We don't know the translation, but the translation happens to be the same as the source word, which can happen quite often, as you can imagine, in science or in medical texts. Sense error is what you would expect. We know the source word, but the translation that should be there isn't in our phrase table, and score error is everything else. Actually, you shouldn't trust score errors very much, exactly because everything else falls in this category. And as you see, like, scores errors actually should correspond to almost a quarter of the errors, which may be true, but definitely you see that the picture is interesting, that when you go from old to mixed, the percentage of score errors doesn't change very much. But it increases a lot in the scene and sense categories. So in the old domain, you have 10% of scene errors on science, and you have only 5% of scene errors in the mixed table, suggesting that if you add the translations from the new domain, you reduce the out-of-vocabulary rate to half. We also have developed a tool that allows you to look at individual translations and visualize the errors made by the system. Okay, so this concludes the analysis part, and now phrase sense disambiguation. This is something that I worked on. As I said, I implemented it in Moses and integrated into the MT pipeline. So, what is it? It's a discriminative context-aware translation model. Basically, you ask the decoder, given these features that are extracted from context, what is the most probable translation of this phrase? This technique was originally developed by Marin Karpoat and Decai Wu, and this is what we did. We integrated it into the decoder so you can use it, and we also tried to implement various domain adaptation techniques using this phrase sense disambiguation. So the normal the normal phrase-based pipeline works like this. We have all these parallel data. We do word alignment, extract the phrases, and then we translate the error. We translate the input, but we of course get an error because this is a motivating example. You can translate rapport from French into English as report or relationship. Now, in this sentence, notre rapport means our report, but we translate it as our relationship because presumably our relationship is more frequent in the data than our report. But there's this word, rédiger, wrote. So this should give the machine translation system a clue. This is not a relationship, this is a report because you don't write relationships. Most of the time, at least. So the decoder has, of course, no way of using this word because it's okay, let's assume it's beyond the context of the language model, and it's definitely beyond the context of the translation model. So what do we do with PSD? We extract phrases from the training data, but we extract them in context. So we also remember that rapport, when it was translated as a report, was surrounded by words like rédiger and other words, possibly. And also when it was translated like relationship, there were different words in the context. And we extract features from these. And hopefully, when we train the classifier and ask it for prediction on this sentence, suddenly the translation will be correct, because the classifier will pick up the word rédiger and will decide to boost the score of this translation. So what features did we actually use in PSD? This is the example context, and this is the example phrase pair that I'm going to describe the features on. So what features do we have? Source indicator, this is just a feature identifying the source phrase, a feature identifying the target phrase. Then we can decompose the phrase into words and add those as features, similarly for the target side, and then we also extract the context. Other features include phrase pair features, using the source and target phrase and the alignment inside them. We can extract paired features, which describe the correspondence of the words on the target and the source side. And the scores features can be also used. We discretize them and take the log and also use those as features. Then how do we train the classifier? Well, WebIt is a very fast, scalable, open source machine learning toolkit. It's an online learning algorithm. It's a linear learner, so it basically gives you a set of weights for the features. And it implements various reductions to support multi-class and multi-label classification. In our setting, we do multi-label classification, meaning that each translation, we can have multiple correct translation options, and we can have a discount for, like a penalty for the wrong ones. So we started with a simple scheme, just the loss is 0 for the correct phrase and 1 for everything else. And we are also experimenting currently with using 0 for the correct one, but using blue we can estimate how similar the other candidates are, and if the candidates are quite similar, we don't have to discount them as much, so they don't get the maximum loss, but they get loss between 0 and 1. And these are training examples then for the classifier. I'm going to go maybe into too much detail, but we had two namespaces. One is the source namespace with the source side features, and target namespace with the target side features. These are the label-dependent features. So each target phrase has several features, and these depend only on the phrase. And what we do then is we use the quadratic features in WebIt to, yeah, it's a funny name. So to get the Cartesian product of the source and target features. So we basically combine each feature on the source side with each feature on the target side and add those to the feature space. And then the decoder, the classifier will simply be given, at decoding time, it will be given the source side and all of these possible target sides, and for each of them, it will loss. How bad is the translation in this context? Okay, moving on. How did we implement it in Moses? So you can actually use phrase sense disambiguation. It's implemented for phrase-based and for hierarchical Moses. WebIt can be linked with Moses as a library. Actually, WebIt wasn't a library before the workshop, but Heldome added the interface, so you can now use it like that. PSD is integrated fully in training and decoding. It has a really nice and extensible interface for creating new features. One minor point that I would like to mention here is you don't actually have to do phrase sense disambiguation as we do. This means that you have a classifier in the decoder that you can use for any purpose you can think of. And if you use our features, you will have phrase sense disambiguation, but nobody's stopping you for developing features that will model like morphology or whatever, and you can just think of it as a generic tool that was added to Moses, and that enables you to do various kind of classification tasks in the decoder. It is also fully integrated in experiment.perl, which is a system for managing experiments. And we had to work a lot on parallelism, both in training, where we parallelized the processing by using multiple processes or even multiple jobs on a cluster, and in decoding we use multithreading. It was necessary because we actually process a large amount of data, and especially Hyro has a lot of training examples. That's like hundreds of gigabytes of data that you need to process. And, well, of course, classifier predictions are features in Moses. I'll just mention Hyro briefly because I want to talk about it further. It was harder in every aspect. I didn't work specifically on Hyro. I worked on the shared code and on the phrase-based specific code. But Hyro is just hard. There is much more ambiguity. You have multiple source rules mapping to each segment. You have multiple target sites. The implementation is more complicated, and the computational resources, you need just much more computational power to do hierarchical translation. But one nice thing that we could do is include soft syntax features thanks to PSD. So the features that would normally be like hard syntactic constraints can be added to, for instance, disambiguation to the classifier as features, and basically you can do soft syntax using our approach as well. How do we do it in decoding? Well, it's a feature function. In Moses, scores depend on the source context, naturally. So we had to do quite a lot of hacking around, including this feature function in Moses. It's integrated in the log linear model. The weight is tuned, which is what we should do. And the scores are calculated before decoding. This is important because it saves computation, like repeated queries to the classifier. And also the initial pruning, just when you load the phrases, can already include the PSD scores. That's one advantage. And also this was quite challenging because one lesson that we learned during this workshop is that Moses is just a very complex piece of software. And if you want to develop something sensible, something larger as a team, it's hard to coordinate. It's hard to implement everything correctly. So actually, I think that one of the lessons I learned is that research in MT is not so hard. I mean, you have to have the right idea, but you also have to have a lot of patience to implement it correctly in the existing systems. And the scores are included in this form, so we get the loss from VW, we take the negative of that, we exponentiate it and normalize, and that's kind of the PSD probability of translation given the source phrase. So how does PSD perform? Well, as you can see, the baseline is very strong. I can tell you what the baseline is. That's the most frequent translation. So you look at both Hansard and science. You take the most frequent translation of each source phrase, and you just output this as the translation candidate, and you already get almost 70% accuracy. So improving this is hard, and we did improve a little bit, but we kind of hoped for more. Well, what can you do? And one nice thing about this table is if you only take Hansard as the training data, this is evaluated on phrases from science. But if you only take the data from Hansard and train PSD on this, you will be able to achieve similar accuracy on the science data as if you trained on both. So this is kind of like indirect evidence that PSD might be more resistible to domain shift, might be more robust in this. That's a good question. Yeah, I don't know. So the baseline takes the most frequent scores from the concatenation of the data, and I don't have this baseline. I tried to find it, but sorry.
What are the representative phrases? Like these were manually selected, and how many?
Right. This was actually a whole sub-project at the workshop, getting the representative phrases. We worked with, I think we started with TF-IDF, but then Katie did a lot of fine-tuning and a lot of really really good work to get representative phrases. The idea is that they shouldn't be the rarest ones, like the singletons in the data, or the ones that are just incredibly rare. And they also shouldn't be the most common ones, like phrase of the. You don't really care about its translation. There are like hundreds of possibilities because of the alignment errors. And so this doesn't really tell you much about the classifier. You want to get the scores on the phrases that you care about, the representative ones.
So it's like an automatically selected large group of representative phrases. It is not a small list.
No.
That would be particularly difficult to the human eye.
No, it's automatically selected.
And also, you don't care about the little formal differences between phrases. Because if you have a phrase of 2 words that has to be translated in a specific way, and then suddenly in your phrase table, these 2 words happen to be within a phrase with a different article or preposition, this would be a different phrase for this type of application.
Yes, it would. Okay. And evaluation of end-to-end empty pipeline, well, that's what we were there to do, right? To improve machine translation with PSD, and we didn't. So tuning consistently gives our phrase and disambiguation feature a small negative weight. If you want it to be snide, you would say that PSD is both misleading, because it gets a negative weight, but it's also useless even though it's misleading. It's not misleading enough. So if you got like a large negative weight, it would probably improve the blue score, and it would be kind of sad that we implemented the exact opposite, but but we don't have even that. So and we experimented with a lot of stuff. We found a number of bugs along the way, but they are gradually less and less important. And we don't have an improvement so far. And now we are trying to do some feature selection. Like, we have a lot of features you saw back here that you have a number of. This generates actually a large number of features. Same with the score features, because these are buckets of. Each score will generate a number of these features. So maybe the classifier just can't pick up the important features. But we're still experimenting with it, and hopefully we'll get somewhere. Okay, domain adaptation. So this is what it's all about. I mean, that was, I think, at least for me, this was the main, like the main idea behind the workshop. Develop PSD, integrate it in the decoder, and then use domain adaptation techniques from machine learning to improve domain adaptation. So we looked at 3 different adaptation techniques. One is really frustratingly easy. You just take the features that you get from the data, and you duplicate them in the old domain. You don't only generate the feature f, but you also generate a feature like old underscore f. And in the new domain, you do the same, and then the classifier can learn which features can be shared and which have which can help you in both domains, which are generic, and which are domain specific. I was thinking about an example, and the only one I found is not actually from MT, but let's say about if you want to classify the polarity of user reviews, and you have like reviews of restaurants, and that's your old domain. And you have something like great value, so you extract feature like a great value, and that's presumably a good feature for any domain. And then you extract features like large servings, maybe. Well, then you want to use this classifier on a new domain, let's say cell phones. Well, this is still valid for cell phones, but this isn't, right? Because well, even if you forget about servings, you don't want a large cell phone. Well, maybe now you do already, but maybe you want a tablet even. But but it used to be the case that you wanted a small cell phone. And so what you would learn is that great would get a big weight as a general feature, and large would get a big weight as fold, as the old domain feature. And so this is a natural way for the classifier to learn which features, as I said, are shared and which are not. Another interesting domain adaptation scenario is using an old domain prediction feature. In this case, we don't use the data directly, the old domain data, I mean. We train a classifier on them and only use the prediction of the classifier. So we let the old classifier predict on our new data, and then use this prediction as a feature and train the new classifier along with it. We can use just the prediction, like the argmax, or we can use the score as well. And instance weighting is also an interesting approach. So you train a binary classifier to distinguish between old and new domain. You take the same features that you would want for your classifier that you're trying to develop eventually, like the PSD classifier. You take the same features, but you annotate them not with labels like with the correct translation, but just by saying this is old and this is the new domain. And you find a classifier, and then you classify the old training data using this classifier. And what you get is a similarity to the new domain. If you get a positive score on the sentence, that means that the classifier was not able to distinguish this old domain sentence from your new domain data. So you get a larger weight here, and this is going to count more when you train the final classifier. Okay, the results are, again, not very encouraging. You probably expected already. The old domain has the accuracy on an unseen def set 73%. The new domain only classifier has 77.92. And then you have all these domain adaptation techniques in between. Basically, sometimes they outperform the new domain only, but only by a little bit. So science just corresponds to taking your small new domain data and training the classifier only on that. And if you do a domain adaptation scheme to also include the old data somehow, you don't get much better, which is kind of discouraging. But that's what we found. Well, and that's it. That's the end of my talk. So thank you for your attention.
So there were some questions. Thank you very much. There were some questions during your talk. There have been some questions during the talk. At least I can correct my grammatical errors. But I hope that there will be some more questions in this question period.
If I continue with my questions, then again, the representative phrases, how long are they? Because the longer they are, the more informative are they on their own. So if these were like short single-word phrases, then the potential of getting some improvement from the surrounding words is much higher. So the features that you use might be more informative. But if you,
yeah,
you know.
I don't know. I don't have the data. Sorry. Yeah.
So when you talk about the context, so from the slides it seems that the context means one sentence, is that right? Yes. So you basically assume that you can guess the domain from the sentence or something.
Well, I kind of assume that I know the domain. I want to guess the correct translation from one sentence.
Yeah.
But we did the work also on document level features and topic related features. And I think I wouldn't have time to present them here, but apparently I would have. So that was a mistake, maybe.
Yeah, so I just, did it help edit or not?
Yeah, I don't think we did an end-to-end empty experiment.
Mm-hmm.
I know that including topics, for example, improved the perplexity of the lexical weights, which is like a hint that it could work, they could help, but we didn't run the experiments. We will, definitely. So.
Okay, thank you.
Thank you for your talk. And you mentioned that you're going to filter that huge feature space. So what kind of filtering are you going to introduce?
Okay, so let me go back to the features. Yeah. So we can do a lot of things. We can, for example, shorten the context a little bit. We also, it's missing here, but we also use the bag of words features, simply all words in that sentence. So we might discard this feature as well. We might not use the morphological tags. We might do some different bucketizing or some different discretization scheme on the scores, and and we can simply remove a whole classes of features as well, like doing feature ablation.
What about some similarity measures, like some clustering based on mutual information? Are you thinking about something like this?
You mean between the translation options of the phrases, or? Between the source sides?
Yeah, on the source side. I guess. Yeah, we can talk about it later.
Okay, let's talk about.
So perhaps one more, or
My question is very naive.
I've just one suggestion, and it seems that I forgot it now. What was this suggestion? Yeah. So the you had the macro evaluation, and then one more type of evaluation. What would also be interesting would be like micro evaluation, just looking at the output sentences and underlining words that you don't like, and manually checking whether the word was mistranslated because of which of the four S's. So did anyone in the workshop do this on just a handful of sentences like that?
So we did have some Turkers, and I don't actually know if they did this particular thing. I would have to check. So we can talk about this later.
Just my naive question. It may be a follow-up to what Andrzej said. How do you decide what's the phrase? I mean, what else? The extent of the phrase?
Yeah, so phrases are actually if you train the system, like if you look at your parallel data, then you can extract a lot of phrases from the sentence. So for example, in this phrase, do not know, we might have also phrases like just do not know, and do not know. We could extract all of these, and it depends on the word alignment.
I decided not to ask.
So anybody else?
Related question. The S4 classification, I can understand how it can work on words, but it was done on phrases, actually.
Yes.
So in that case, for example, let's take your example, write a report. Mm-hmm. The word report itself, it's ambiguous,
yes.
Or the French word for it. So it sends. But if you take whole write a report as a phrase, then it may be scene error because you haven't seen this in your training data in the new domain. So now the same error, is it classified as scene or sense or?
Yeah, this would be classified as scene. So yeah, I think.
And if the decoder decides to pick not such a long phrase but only report as one word phrase, then it would be sense error. So the classification is depends very tightly on the decoder use and how long phrase it chooses.
Yeah. Yeah, because that's interesting because the scene error really corresponds to phrases, as far as I know. I'm pretty sure of it. So it doesn't matter if there are like known or unknown words in there. It matters whether the whole phrase was seen in the data. Yeah.
I've read the paper, which is not published yet, and I couldn't even formulate this question properly to ask you before this talk. So okay.
I may, perhaps to conclude, if there are no other questions. So in general, what you have learned during the workshop? You've already mentioned that Moses is a complex piece of software, which is kind of double-sworded X. And
yeah. Yeah. So well, there was. I mean, results so far are not very encouraging. So. We did a lot of work during the workshop, and we really implemented a lot of stuff, a lot of techniques, a lot of various approaches, and the results so far are not very promising. But so lessons learned. Well, lesson for myself is like always check my code 5 times before I before I run it, because I tend to make really small errors that are found later than to big surprise of everybody. Yeah, but
what big and little tricks could we learn from people like Hal Daume or others?
I don't know. He didn't actually talk so much during the workshop. He spent most of his time like hacking Baupau a bit and trying various schemes for the reductions and things like that. Yeah.
Yeah, I spent also a lot of time on Baupau a bit, and so I would like to announce that in a few days there will be a Perl wrapper to Baupau Webbit available. So
maybe you can get as good results as we did.
There are no questions any longer. So thank you once more for your talk and for giving us this picture of your experience. And I'm looking forward to see you all next Monday.